Hello, greetings from the Astronomical League of the Philippines. I am Dr. Jet Aguilar, and I will be hosting today's webinar. Thank you so much for joining us for our 2024 Astronomy Expert Speaker Series. I am very happy to welcome all our attendees, not only from the Philippines and Southeast Asia, but also from all the other parts of the world. Today, we have another very exciting and interesting topic to be discussed by none other than Dr. Peter Jenniskens, a meteor astronomer with the SETI Institute and NASA Ames Research Center in California. Early this month, some of us were fortunate enough here in the Philippines to witness a meteor fireball over northern Luzon Island, Philippines. Dr. Jenniskens will discuss about this meteor asteroid 2024 RW1 and the importance of small asteroid impacts. My colleague from ALP, Mr. Edwin Aguirre, will be introducing our esteemed speaker later. For those who are not able to register, but who still want to watch this presentation, we are currently live streaming on Facebook at Facebook page of the Astronomical League of the Philippines, where you can view this webinar live. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable and learning experience for all. Please listen and do your best to give your individual attention to our speaker. There will be a short question and answer session at the end of the presentation. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We'll do our best to answer your questions live after the lecture or via the Q&A tab. And we would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present with us throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. Enjoy and let us all have fun learning. Here's the program flow for this webinar. May I now turn you over to Edwin to introduce our esteemed speaker.
Thank you very much, Jet. Before I do the introduction, I would like to offer our sincerest apologies for the typographical error in the previous slide. So we apologize to our speaker and to our audience in the error in the name of speaker on the slide. So we hope for your understanding. Thank you. Now, it is my great pleasure and honor to introduce to you tonight our distinguished speaker for our Astronomy Expert Speaker Series, Dr. Peter Jenniskens. Dr. Peter Jenniskens is a meteor astronomer and research scientist with the SETI Institute and NASA Ames Research Center in California. He is an expert on meteor showers and meteorite falls, and is the author of the books Meteor Showers and Their Parent Comets, published in 2006, and Atlas of Earth's Meteor Showers, published in 2023. You can get copies of these books from Amazon.com. So I hope you get a copy. Now, Peter is the principal investigator of the Cameras for All-Sky Meteor Surveillance, or the CAMS project, in support of NASA's OSIRIS-REx mission. He was also the principal investigator on the 1998 to 2002 Leonid multi-instrument aircraft campaign, and the 2004 Genesis, 2006 Stardust, and the 2010 Hayabusa aircraft re-entry observing campaigns. Peter is best known for his recovery of fragments of asteroid 2008 TC3 in the Nubian Desert of northern Sudan with Sudanese researchers from the University of Khartoum. This was the first time that an asteroid was spotted in space, observed by telescopes then samples retrieved on the ground for study. Peter also identified several important mechanisms of how our meteor showers originate, including identifying the parent body for the quadrantids, which is 2003 EH1, as well as several others. Now, these are examples of how fragmenting comets are the dominant source of meteor showers. Peter received his PhD in physics and astronomy in 1992 from Leiden University in the Netherlands. Asteroid 1999 TY224 was named by the International Astronomical Union as 42981 Jenniskens in his honor. Ladies and gentlemen, please welcome our speaker for tonight, Dr. Peter Jenniskens.
Thank you. Thank you very much for this nice introduction. You've got a quick preview of some of the slides coming. Yes, Asteroid 2008 TC3 was the first time that an asteroid was seen in space. It was tracked and the impact point calculated. And this was back in 2008. And I teamed up with Maui Shaddad from the University of Khartoum and his students, and we scoured the desert and we found pieces of it. And that was, the first time we had a sample of an asteroid that was seen in space. Just 3 weeks ago, we had another one of these asteroids that was tracked. It was predicted to impact close to Luzon Island in the Philippines. Big reason I'm talking to you today. And sadly, that one ended up over the ocean. So unsure if we will ever succeed in recovering material from it. But we've now have 4 of these cases where an asteroid was spotted in space, tracked, and pieces found. First one was 2008 TC3. Second one was 2018 LA, which Botswana, in the Central Kalahari Game Reserve. So that's a place where you go to see lions and giraffes, ostriches, elephants, you name it. Then in 2024, last year, there was an asteroid impact in Normandy in France, 2024 CX1. And surprisingly, we had another one earlier this year in Germany, 2024 BX1. And when these events happen, I team up with local researchers. So this was Mawia Shaddad at the University of Khartoum in 2008. In 2018, I teamed up with Oliver Moses at the University of Botswana in Moon. And 2023, that should be 2023 CX1, I teamed up with François Collin at the Observatoire de Paris in Paris. And in the beginning of this year, I teamed up with Lutz Hecht, who's a professor at the Museum für Natuurkunde in Berlin and the Freie Universität Berlin. And in all cases, we managed to find pieces of these little asteroids. And it's quite a feat. I've been able to be present with all 4 events. So I'm very proud of that. I hope that we can continue this in the future, but who knows. And as you can see already in the first interesting case in Sudan, we were using aluminum foil to collect the meteorites. We do not want to touch the meteorites. So one of the important things about these small asteroid impacts is that it is possible to collect meteorites very quickly after the fall and to collect the meteorites pristinely. So you can do studies that you can't do when the meteorites have had a long journey
the ground to the laboratory. So no touching, but use a piece of aluminum foil to handle the meteorites. The no touching is because you have your hands have salts in them, and when you touch a meteorite, meteorites are often very porous. They really suck in all the moisture, and with it, amino acids and all sorts of other compounds. And so, of course, we want to see what's really in the meteorite in space. So this is sort of a poor man's sample return mission. There have been 3 sample return missions successfully executed in the last 20 years, 30 years. This was first, of course, the visit to the Hayabusa 1 mission to Itokawa, which brought back a few grains of LL5 ordinary chondrite from asteroid Itokawa. And recently, we had a mission to Ryukyu and a mission to Bennu. They were thought to be different asteroids. They had slightly different reflection properties, but upon return of the samples, both proved to be CI carbonaceous chondrite, and the CIs are very rare, very pristine, very precious. So I'm sure both missions were very excited with the results that they had. But it was a little bit of a surprise that both came out to be CI carbonaceous chondrite type. In the meantime, the students have not sat still, and more people have helped in finding these small asteroids seen coming in. 2008 TC3 was the first one. That proved to be a urealite, which is an achondrite. It's a very rare type of meteorite to find. And this also proved to be just incredible object, incredible fall, because it was a mixed bag of things. It was not just urealites, but lots of ancestite chondrites, ordinary chondrites, and whatnot. We've had 9 of these impacts since 2008 TC3. There have been 4 overland, and all 4 we were able to recover. So 2018 LA was the 3rd one, and that proved to be an HED, which is a howardite eucharite diarchenite. It's the type of meteorite that is associated with asteroid Vesta. Very interesting case as well. And then in last year, we had this fall in France, and that proved to be an L6 ordinary chondrite. It's the very first sort of ordinary chondrite we've had. And then the one earlier this year was an aubrite. And aubrites are also very rare achondrites. In this case, 1 in 1,000 meteorites are of that type. So we've been, it's been an interesting haul, and every recovery has its own story and has added information to what we know about these meteorite types and about their origin. So 2008 TC3 is still my most fun adventure because it was my first experience visiting an Arabic country. It's great to experience the culture, meet people at the University of Khartoum. It was fantastic to go into the desert with the students, and very exciting to look for meteorites from an asteroid that exploded so high in the atmosphere, 37 kilometers, that nobody had ever found meteorites from an impact that high up. But this was a big object. This was the size of a small car, about 4 meters in diameter, 6 by 4 by 2.5 or so. So this was a big object, and even if a tiny scrap of material survived, one could still hope to find meteorites. And we went looking, and it took Mohammed Alamin, student at the university, geology student, only 2 hours to find the first meteorite. And that was just very exciting. And then when more and more meteorites were being found, they all proved to look differently. And we've been going back to these meteorites in recent years and investigated their nature, their identification, with work by Serena Goodrich, who's an expert on urealites, the specific meteorite type that TC3 was dominated by. And she found lots of other things. As I said, we doubled the number of ancestite chondrites in the world by just this one fall. We've had lots of interesting ordinary chondrites, and very excitingly, we've found some carbonaceous chondrites in this interesting asteroid. So all of this stuff was part of this one little asteroid that came into the Earth's atmosphere, fell apart in pieces, and landed on the ground. So this was a CI sort of a carbonaceous chondrite. So maybe related to the material that that was brought back from Bennu and Ryugu. Very interesting meteorite. This one also had a little clast of uralites in it that we've not seen with other meteorites. Most other meteorites were really distinct types. So this was exciting. And then this one was really weird. You know, another little sample of the origin period of our solar system when things were gathering, were colliding with each other, were accumulating fragments from all over. And you're seeing some stuff here that is not seen in other meteorite collections. So that's rather special. So we have a window on the early time of the solar system. This is the area where we found the meteorites. It's very close to a railroad line and a station number 6, hence the name Al-Mahatasita for the meteorites. All the meteorites were found in a very narrow strip. But the meteorites, the bigger pieces, were found in a much wider area, and that was sort of curious. So you can see the strewn field was incredibly big. The asteroid came in at a shallow angle. So the scale bar there is 10.4 kilometers. So this was a lot of walking. Fun doing. We did a lot of vertical scans to really get a good sense on how wide the strewn field was, as well as try and collect as many meteorites as we could. So Maria has gone back with his students for several of these trips over the years, and over 600 of these meteorites were collected. And so if you look at the distribution, you see that the small pieces are sort of 0.7 kilometers wide dispersed, and the big pieces are much more widely dispersed. And that's really a characteristic of this fall, and that sort of piqued our interest, is asking why is that. And we built models. This work by Dale Robertson and NASA Ames in the Asteroid Threat Assessment Project group, where the shape of the asteroid, which we determined from the observations of the asteroid in space, was used to then look at how does the atmosphere interact with this rock. And as you can see in the beginning part, it looks quite normal, quite organized. But then at the very end, suddenly, it completely breaks apart and things go flying everywhere. And I think that's the key thing. So once, as long as you keep that final piece at the back of the asteroid intact, then all the fragments sort of flow along with the flow field. But once you start creating all these bits and pieces at the very end, then you get shock interactions. This was actually demonstrated in laboratory experiments where the pieces expel each other, and that creates a much bigger transverse velocity. So this is how we think now a little asteroid coming in the Earth's atmosphere finds its demise. So initially you melt a lot of material, you vaporize material, then you get deeper into the atmosphere, you reach a point where you basically exceed the strength of the object, and things start breaking massively. But as long as that final bit at the back of the asteroid stays intact, things just flow along the flow field, and you end up with stuff falling in a very narrow strip on the ground. So the narrow strip is sort of the stuff in the center. And then that last bit, that last piece that suddenly explodes, literally sort of hits the wall and breaks into many pieces, and then the pieces expel each other. That leads to the high transverse speeds and to these bigger chunks that are found at the end of the strewn field. And we can say that's the way it happened because when you look at the distribution of the pieces on the ground, you can see that the big piece broke, the back piece broke when it had already slowed down a bit. So this was really towards the end of the meteor path. So that's something new we learned. We learned new things about asteroid impacts, about the physics of how these objects enter the atmosphere, aside from having these really unique samples of our early solar system. So, I keep an eye on these things. It's very exciting when they happen. And 3 weeks ago, we had an asteroid called 2024 RW1 that impacted just near the coast of Luzon Island in the Philippines. This was the message that was sent to my email box at 11:42 my time here in California, just before midnight. Of course, I was sound asleep. And there was mention of that there were 4 observations made by Catalina Sky Survey in Arizona. And if you quickly check all the numbers, so what's interesting is that it was a small object. The H means the brightness of the object, sort of between 19 and 34. These small things are sort of 32, 31 so it's in that range. Pretty big impact probability for just 4 observations, so that's really interesting. And then it says geocentric orbit score is 1, which is the thing at the bottom. That means that if it's 1, it's very low. That means that it's not likely a geocentric satellite. So it looks like this is a real asteroid coming in. These announcements, so based on only 4 observations, which is very little, come in from the NASA Scout project and from the ESA Meerkat asteroid card. So those are 2 programs that look at these really early reports of an asteroid spotted in space, and then evaluate whether this is an interesting asteroid, whether this asteroid could be something coming close to the Earth or could actually be an impactor. And you can get registered for that, and then you can get these emails. And that night I was sent an email, and so then about half an hour later, this was the report that came in based on just a few observations. Dave Rankin at Catalina Sky Survey already mentioned this object looks real. So we are working to have follow-up. So we're going to try and do more observations on this asteroid and try and get a better track on it. And as you can see, this is sort of the Earth, the globe. The reason you get a line is because even at 4 observations of the asteroid, you have a very nice definition of the plane, the direction in which it's moving. But you don't know exactly where the asteroid is in its orbit. And so depending on where it is, that decides on, where how much the Earth has rotated at the time when they actually meet. And that's why you initially end up with a line like this. So if the orbit is uncertain, then you're also uncertain about where it could impact. And it could be on the ocean, it could be over land. But as you can see, the Philippines are already on that line. And this was just after 4 observations. And so then other astronomers heard about it and they started observing. This is an observation by team of the International Astronomical Center in Abu Dhabi, Mohammed Odeh. You see the little point there in the center, sort of coming from the top. That's our asteroid. And it's a tiny, tiny little speck of light, but this type of observations is what allows astronomers to get a better fix on the exact orbit. So it's important that your timing is good, that you make sure that your computer clocks are properly set up. And in this case, the asteroid was followed. We found that in some of these cases, it's actually better to just let the asteroid travel through the field. So you can, because if you do that, then you see the asteroid brightness go up and down if it's a fast spinner. And so if you want to get your spin periods and precession periods and so on, then you just want to let it drift through. So this is already now half an hour later, about 45 minutes after the first announcement came out. A couple of more observations came in, and lo and behold, it's confirmed as an impactor, as Marco Michelli was writing, who runs the ESA NEO office, handling with these cases. And so already somewhere roughly around the Philippines. And this was at that time still 9 hours to go. Of course, I was still sound asleep at that time. Well, early in the morning, I was woken and told that something was going on. And by that time, it was already known that this little asteroid was going to impact just east of Luzon. The Minor Planet Center issued an alert at 6:26 my time, where they said that the asteroid had a semi-major axis, which is the diameter of the orbit, if you like, so it's 2.51 AU, and an inclination of half a degree. And I will come later back to that because that got me very excited. And they already gave this thing a name, so now it was designated to be Asteroid 2024 RW1. And of course, then the impact happened. People saw it from Manila, from other parts in the Philippines, and of course from Luzon. And I have a few pictures taken near Santa Ana, at the tip there where the impact happened. And as you can see, this graph is from the American Meteor Society website, that collects these visual accounts so people can report their fireball sighting. If you see something in the sky like this, please go there, because all these accounts help us get a fix on where the fireball was. And even with your general description on directions, you can already get a pretty good track on it very quickly. And so this was seen from Santa Ana. It's just a spectacular view. And what really got me excited was this sort of orange tail you see. That you don't see with many fireballs, but that means there's a lot of little glowing debris coming off. And together with the orbit of this thing, I'm guessing that this was a CM2 type carbonaceous chondrite. So it would have been nice if we had a chance to actually recover this material, but meteorites are at the bottom of the ocean. So these impacts happen regularly. The website where you can find accounts of this is the cneos.jpl.nasa.gov fireball site. At the bottom left is the address. It gives some basic information. It tells you that this was a 0.2 kiloton impact. So it was a decent amount of energy. This was not a small object. Meteors, also a size asteroid coming in. And this information is collected from satellite observations. And you can see it's a random process. I mean, these impacts happen all over the globe. 0.2 kilotons is, beautiful fireball in the sky, nothing to worry about, but they can get bigger. So let's take a step back for a second and just let's sink in how little protection we have from things coming in from space. I mean, we have, if you stand outside, you look up at the sky, there is just effective about 14 kilometers of air between you and the vacuum of space. I mean, the air becomes less dense when you go up. And so, 100 kilometers up, say, that's sort of where the boundary is for these solid objects. That's where a meteoroid meets its own mass of air and shows the shooting star, the glow, the meteor. 100 kilometers, that's not very far. So space is close. And when you look up at the sky, you're not looking at a dome, but you're actually looking into the universe. In this picture, you see the Milky Way very nicely, and you see also the zodiacal light, this diffuse light that comes from scattered dust in our solar system. And if you take an even further step back, and now not looking from the Earth up, but as a satellite heading out of the solar system, like the Voyager 1 spacecraft did back in 1990, then this is how our planet looks like, the famous blue dot, pale blue dot picture. Just realize that that's your home. That's where everybody you ever knew lives. Everything that ever happened that you're aware of with people, friends, family, parents, all happened on this one little dot. So we are really in space. And what that means literally is this. There are a lot of asteroids around. in near its orbit. So here you see the Sun, Mercury, Venus, and the blue line is the Earth's path. These are all the asteroids we know as of a few years ago. There have been more discovered. All the blue dots are near Earth objects, things that come close to Earth. In the orange in the background is the asteroid belt between Mars and Jupiter. These are the asteroids that are, many of them are small, some of them are big and dangerous. This is sort of a sketch of the solar system as we created it for a study back in 2010 where we showed that it's comets that are responsible for this zodiacal light. And those are the ones that scatter all this dust around. And in order to get the thickness of the zodiacal cloud, you really need to start out with a population much thicker than the asteroids are. And you need to also then have Jupiter stir up the population a bit. But if you look at the asteroid belt, sort of the crosscut section, then sort of see it as this. You have a distance going away from the sun, and you have a distance going out of the plane of the planets. And if you plot those two distances up, so this is the sort of the proper semi-major axis of the orbit, which is proportional to the orbital period. It's sort of an average orbital period, an average semi-major axis the orbit has over a period of time, versus the inclination of the orbit. So how steep is the orbit tilted on the plane of the planets? And you plot each asteroid that we know of on this graph, then it looks like this. And this is sort of, your cross-section of the asteroid belt, if you like. And in it are these groups, these clusters called asteroid families. And asteroid families are basically debris fields. There was a massive collision that broke up a larger asteroid. Usually the projectile is small, the target is big, and you end up with a lot of pieces of debris that have similar colors, similar spectral properties. So if you measure spectra, reflection spectra on all these points, and you plot it then up in colors, it looks like this. And here it's split in sort of the background and the families. And you can see that the families stand out in the colors really well. And there's about as many family members as the background. You see this green color there. That's the asteroid family associated with asteroid Vesta. It's very unique, very unique colors, very strong pyroxene absorption bands, because it's the one basaltic family that we know of. And then there are the orange families, which are the more related to our ordinary chondrites. Those are the S-class. And then there are the blue ones that are more related to our carbonaceous chondrites, which are the C-types asteroids. And each of these sort of debris fields has a name, as a family name, and each debris field could be the source of one of our meteorites. And so we very much would want to do geology with this, understand which meteorite comes from what area. That's sort of an interest in what we're doing by tracking these meteorites coming in and recovering the meteorites. So fundamentally, ancestite chondrites is where the Earth was built out of. That was from the inner side of the solar system. Ordinary chondrites was sort of in between. And then there was a gap, later filled up, Jupiter, and then beyond Jupiter, that's where the carbonaceous chondrites had their origin. So just a brief interlude to get the names for people that are not so familiar. So asteroid is just like a star. It's how it looks like in a telescope. You see this little star moving among the other stars. And it is a small object, rocky object that orbits the sun. There's also a family of starfish, for example, that is the Asteroidae family. That's where the name comes from. It just looks like a star. Meteor is raised, lofty, sublime. It's from the Greek raised, lofty, sublime. So it means it's related to atmospheric phenomena. Meteorology comes from meteor. It's basically used anything in the heavens. It's the light. It's basically the light from a high-speed entry of a solid body in the Earth's atmosphere. That's what your meteor is. There's other names for it: a fireball, bolide. They're all meteors. If it relates to radars, it's the production of electrons and so on that makes it a meteor. There's also a meringue candy that was called meteors for that very same reason. It's lofty, sublime. A meteorite is the product of a meteor. So what survives from a meteor, that's what we call a meteorite. And so a perfume that you put some meteorite material in it would also be a product from a meteor, and therefore perfectly okay to call a meteorite perfume. So what do you look for when you look for asteroids, for meteorites? Here's a couple of examples. You basically have meteorites that are completely covered in fusion crust. They sort of have this roundish shape to them. The fusion crust is visible in the middle picture and is clearly the indication what to go for. It's this layer of glass that surrounds the rock. So when the rock comes in at very high speed in the Earth's atmosphere, then that's what happens. The rock melts. The melt is immediately blown away by the air, and that leaves behind a really thin crust, a thin fusion crust. And that fusion crust can be shiny if there's little bubbles in it. That's what happens with the HED type meteorites, for example. But it's the crust you're looking for. The inside can be dark, can be black, can be white, very light, can be concrete looking. That's not a good indication. Don't hold magnets to them. Some meteorites are magnetic, some are not. If you hold a magnet to it, magnetic signature is gone, and the natural magnetic signature. And so, we want to be able to measure that. So keep away the magnets. Look for this really distinct fusion crust. And so if you send me a picture of a rock that you think is a meteorite, and you do that in daytime, take care that the picture is sharp, then normally you can tell from the picture whether it's a meteorite or not. Not always, but most of the time you can. So how is it to finding a meteorite? Well, one time, this is in Botswana, the Central Kalahari Game Reserve, we were looking for fragments of 2018 LA, and I actually found a piece while I was filming. All right. All right. So that's how you do a discovery. It's not no big jumping up and down and yelling. It's like, oh, that's funny. And of course, then you tell everybody that you found a meteorite, and then the yelling and the shouting and the dancing comes. And then a short while later, your meteorite picture will appear in the New York Times as, this was a very, very cool discovery. So here is a little piece of Asteroid 2018 LA. And in this case, it was a diogenite. And other meteorites we found were howardites, eucrites, diogenites. So they can be a lot bigger than the small asteroids. This is a famous video from the Chelyabinsk impact, which happened in February of 2013.
Нихуя себе, это что такое? О, нихуя метеорит, блядь. Внимание, ебануться. Нихуя себе.
A couple of things to watch with this one is that when it happens, when the thing is at its brightest, you can see there is this glowing cloud of debris and plasma there. And that's, we've never seen in fireballs. So this was a very big object coming in. This was a 20-meter size asteroid moving at 19 kilometers per second. So this was 500 kilotons of TNT deposited in the upper atmosphere. Look at the glow.
Никакой метеорит,
And you can
блядь.
see one piece
И
continues out.
получу. Нихуя себе.
So
Охуеть.
this same glow was also seen in the Tunguska impact back in
Блядь, от меня
1908.
это
So I traveled to Chelyabinsk in the weeks after this event and teamed up with Olga Popova and Slava Amayenko from the Institute of Dynamics of Geospheres in Moscow and the Astronomical Institute in Moscow. Slava used to work in Chelyabinsk, so his office had the windows blown out like many others. We were given a car and a driver by the governor to visit all the various villages, and we mapped the extent of the glass damage. So all the blue and orange points are villages where schools had lost their windows. Schools have sort of a sun-sized windows to them, and so they're very nice measurement of the intensity of the shock wave. And so in this case, the fireball came from the east, traveling west. It reached its peak brightness at the moment where the rock breaks and falls apart into pieces. That's where the atmosphere stopped the rock and where all this energy that is in the motion, this 500 kilotons of energy, is released. And so a small fraction of that goes into the shock wave, and then the shock wave went over the city of Chelyabinsk, which is 1.2 million people, and blew out windows massively. One piece survived and fell in Lake Chebokul. So we were there. We checked the eyewitness accounts. We checked the video records that were taken, calibrated those, and determined the orientation of the trajectory and the entry speed, and measured the energy deposition profile. And pieces did survive from this fireball you saw in the sky. The thing fortunately broke up very high. It was about 30 kilometers up. If it would have penetrated deeper, we would have had the same sort of damage in Chelyabinsk, but more damage closer to the ground. In this case, the really bad damage was prevented by the rock breaking up as early as it did. But the little pieces of rock, the meteorites that were found, did tell us what this rock was. And even the piece that survived and that created an impact crater on the ice, 70 centimeter thick layer of ice on Lake Chebokul, was ultimately found. So the Russians went in, located the meteorite at the bottom of the lake, dug it out of the mud, and transported it to a local museum where it's now on display. So Chelyabinsk was a big rock as far as meteoroids go, but a very small asteroid, 20 meters. Most of the asteroids we were worried about are 140 meters or bigger. But this one already created some damage. The thing in Tunguska was about 50 meters, but came in a lot faster. So had about 12.5 megatons of TNT energy coming in. And so it's really that energy in motion, the Earth moving into a rock. The Earth is going with 30 kilometers per second around the sun. Even if your rock just sits there, that would be an enormous kinetic energy. And that's the dangers that these rocks pose. So the one for TC3 was a lot smaller, it's about that size, and most of the other ones we've had are sort of in the 1 meter size scale. So 1 meter, half a meter. So about 10% of your rock can survive. So these are sort of the fractions of meteorites that can survive. So even when if the entry speed isn't too high, if it gets too high, then you lose a lot of material. But if it's sort of 15 kilometers per second, 14 kilometers per second, then you can have about 10% survive. So from a kilo, you can still have 100-gram meteorite survive on the ground. And such meteors are actually very frequent. We have about 10 of these falls per year here in California. There must be in the Philippines also about 10 meteorite falls of this kind per year. And if we just could recover those, then that would give us a lot more information on meteorites and on what sort of orbits they're coming in. Unfortunately, we only have about 14 times a year that a meteorite fall is reported over the whole globe. So we are setting up cameras to catch these fireballs in the hope that tracking them will help us recover more, have people go look at the places where they landed. I run a camera network called CAMS, which is mostly designed for mapping our meteor showers, and so that's the purpose of that camera network. It's global, but you know, there are camera networks designed for looking at fireballs, at meteorite falls, and so this is sort of the distribution of cameras in the world that cover these. And the Philippines should, you know, become a future place where this also happens, because who knows, there could be another meteorite fall in the future. And these are the various meteorite falls that have been, and the various networks that have been successful. The European Fireball Network, headed by Pavel Spurny, Jerry Bovicka, Lucas Spurny, they have been most successful with 23 cases where they contributed imagery to. The Global Fireball Observatory that I participate in, that out of Curtin University in Australia, is also very successful now with 16 recoveries. And there are various other camera networks that have also contributed. So we have about 70 cases now for which the asteroid is seen coming in, and as in not in space, but as in traveling through the atmosphere. And then later a meteorite has been found, a meteorite recovered. And if you look at the various meteorite types on the right side, we've gone up, the numbers now are such that we have about 26 H chondrites. H means high iron. We have about 20 low iron ordinary chondrites, and we have about 6 LL type ordinary chondrites. And the Jenniskens one was an LL type ordinary chondrite. And then there's also 3 howardites and a eucharite. We have also 5 CM carbonaceous chondrites now. And that data together gives a good picture on, you know, what's going on in terms of in what orbits our meteorites are coming in the Earth's atmosphere. This is the sort of equipment used by the Global Fireball Observatory and the Desert Fireball Network. So when we set up our Global Fireball Observatory camera back in 2015, very quickly we had our first detection. This was very exciting. A meteorite fall in Creston in California. About 6 meteorites were found from this fall. We have a nice track on it, and that was a first result. And then we started observing in earnest, tried for many years, but fortunately again, end of last year, we had another successful case where there were also about 6 or 7 meteorites recovered, called La Posa Plain. And that was an LL ordinary chondrite again, the same as Jenniskens. So this was the first new orbit of this type that we detected. Very short orbit. So this particular orbit, so we see the meteoroid travel through the atmosphere for just a few seconds, and that's enough to trace this pad back into space and get the pre-impact orbit. And in this case, the object had not gone at its furthest point just past Mars. So it did come out of the asteroid belt, but it had evolved into a shorter and shorter orbit over time. And that seems to be something typical of the LLs. If you look at the green one, you see all the LLs come out in quite a bit shorter orbits so far than the Ls that we're the L-type ordinary chondrites. We also started to see a pattern with the CMs. They seem to be more eccentric orbits, and they seem to come out of the 3-to-1 resonance. This is back in 2018. And so this is what we're looking for if we measure the orbit of a meteorite coming in, and we try and figure out what does it tell us about the source region. We're looking at the semi-major axis, which is how long does the rock go around the sun, the orbital period. And we look at the diameter of the orbit, if you like, and we're looking at how steep is the orbit inclined to the plane of the planets. And so inclination is here vertical, semi-major axis is horizontal. There are resonances, that is orbital periods that resonate with Jupiter, like the asteroid goes around 3 times when Jupiter goes around once. that sort of resonances are very dangerous. If a rock ends up in one of these resonances, then the orbit changes very quickly, and then it can come close to the Earth. And when it comes close to the Earth, this is how the orbital elements distribution looks like. And you can see from the red areas, they are sitting around 2 AU, where there is what we call the nu6 resonance, and then there is around 2.5 AU, where there is the 3-to-1 resonance. Those are the two delivery resonances. So when the rocks hit the Earth, many of them still have the CMU major axis of that resonance. So that's the first thing we're trying to do, is find that resonance. And the other thing is, you can see that if the source is low, has low inclination, if we start at low, then you will end up hitting the Earth in a low inclined orbit. Except if you're in the inner main belt, low, then you do tend to have interactions with the Earth over time, and that sort of brings up the inclination, and so you get a much wider dispersion there. And the effect is stronger if you're really low in the atmosphere, in the asteroid belt, as in the left plots. In the right plots, if you're a little bit higher up at 10 degrees, then that effect is not as strong. And so these are all the various asteroid families that we are interested in. And for the LLs, there is actually one asteroid family that sits right on the inner side of the asteroid belt, where stuff would come on orbits that are very short. And that's the blue family here, called Flora. So Flora family is likely the source region of Chelyabinsk and the source region of our LL chondrites. And so we're trying to do that for others. And so, as I said, I was very excited when I heard that this particular object had a CMU major axis of 2.5 AU and an inclination of 0.5 degree, because that's a characteristic of CM2 ordinary chondrites. And I had one case here in California called Sutter's Mill back in 2012. Found some pieces of it very quickly after it was found. Robert Ward, the meteorite hunter, found the first piece, and I found the second. So we had this analyzed and measured the orbit of the asteroid coming in, and it fell around the 3-to-1 resonance. And since that time, we've had Windscombe, and we had Maribo and Akazarkas, and they all sort of sit very low inclination, below 3 degrees in the asteroid belt, and sort of near the 3-to-1 resonance. And that means that that's our delivery resonance. And so if you then look at primitive asteroid families in the area, we are really too low in the asteroid belt for Polana and Sulamitis in the inner belt to be our source. Veritas and Koenig are really too high up as well in inclination. Our source has to be low in the asteroid belt, and it seems to be that there's an asteroid family called Themis sitting in the outer main belt. That looks to me the most likely source for these particular meteorites, CM on carbonaceous chondrites. They don't survive the inner solar system very long. They have all very short cosmic ray exposure ages. That means that how long after a collision they are exposed to cosmic rays. We can measure that, because the longer they are exposed, the more you build up these radioactive elements. And so in this case, the exposure is always very short, always a million years or less, 2 million years at most. And so these rocks break apart, they fall apart. And as a result of that, you often find them still with the CMU major axis in the resonance. Now, we also had an object called Flensburg, which was a C1 ungrouped. That one is actually high enough inclination that it could have come, in my opinion, from the Veritas family as an alternative source. And that one seems to have been delivered by the 5-to-2 resonance, not the 3-to-1. And so Themis, when you're looking at your plot, Themis is that brown, but is the red area between 3 and 3.5 AU CMU major axis, sitting very low inclination. That's where the Themis family is. So I think that's where our CMs are coming from. Now, the other group that we got a lot more insight over is H-chondrites. The H-chondrites plot of inclination versus CMU major axis has a lot of objects cluster just past the 3-to-1 resonance at very low inclination. And there's now 2 of those that have the 7 million year cosmic ray exposure age. So the graph here showing all the cosmic exposure ages that all these meteorites have, has a peak at 7 million years. That peak, that means there was a big collision somewhere. I'm trying to find where that is. It looks like that happened very low inclined, somewhere past the 3-to-1 resonance. And as it happens, there is an asteroid family there called Coronis, and Coronis has H chondrite type spectra. It's an S-class asteroid family, and there is a family there called Karen that is about 5.8 million years old. So there we can actually still see the breakup debris. So there was a lot of bigger stuff aside from the small stuff we're now seeing as our meteorites. There was also a lot of bigger stuff, and that family is recognizable. There's also another family called Coronis 2, is about 15 million years. And I think we can see that in our cosmic ray exposure ages, because the few ages we have, correspond to these 7 million year cluster. Those are probably from Karen, and then that whole group. We have to measure all those cosmic exposure ages to decide if they could all have come from Karen. But then there's this one case called Hamburg, the Hamburg meteorite, which comes out at 12 million year cosmic ray exposure age, and that could have been a piece of debris coming from the Cronus 2 cluster. There's even another asteroid that's 83 million years old. By that time, the families become more diffuse, and so maybe one day we'll find that group of asteroids as well. This is the L chondrite, the low iron chondrite group. It's much more dispersed, and so there's not a recent impact. Indeed, if you look at the cosmic ray exposure ages, you see there's a wide range of events. There are many collisions that contribute our L chondrites, and from the sort of large distribution of inclinations, you can see that the source is probably low in the asteroid belt, and it's probably low in the inner side of the asteroid belt. And where exactly that is an ongoing debate. There's two candidate families actually that are our likely source. There's Massalia family, that's the orange one at the bottom in the inner main belt, and then there's this red group called the Mildred family. L chondrites have this 470 million year argon-argon resetting age. So there was a collision that happened 470 million years ago. Both families seem to be a bit too young to account for that, but my opinion, the Mildred family may be underestimated. So, as it stands, they could come from both. Then the HEDs, those are the meteorites from Vesta. Vesta meteorites, there's this big peak around 22 million years. So there was a big collision that happened 22 million years ago. And in this case, we can play a very interesting role because Vesta is such a big asteroid, and Guy Conzermagno talked about that in a previous talk in this series, that Vesta itself, the surface of Vesta, is actually the better target, the bigger target for big impacts. First time when we noticed that was when I studied the HED that fell at Sarıcicek in Turkey with a project with Ozan Unzalan from Ege University. And again, we do these massive studies and really try to understand this rock and where it comes from. And when we looked at the ages that were measured for the various craters in Vesta, so you see here's the crater Antonia. So we think that Sarıcicek came from this crater. And that is because the greenish colored area is freshly ejected stuff from the crater called the ejecta blanket. Once the ejecta blanket gets deposited, small asteroids start impacting it, and you create new small impact craters. Count those craters, and it tells you how old the impact was. A lot of craters, a very old crater, few impacts, young crater. Of course, you have to calibrate the scale, and there's big debate about it, but the lunar chronology scheme seemed to work in the sense that it actually identifies the various peaks that we're seeing in the cosmic exposure age. So here I've plotted that sort of in one graph. I've plotted the age of the crater in vertical direction, also the cosmic ray exposure age of the meteorites in vertical direction. And then horizontally, I've plotted the size of the crater. So it's the biggest craters that give us the most meteorites. And so those are the likely sources of our meteorites. And if you compare that with the number of rocks we found, then you see that the 22 million year exposure age of Saricicek agrees with Antonia in the black points, which is the lunar chronology scheme. But it doesn't agree with any of the craters in the asteroid chronology scheme, where the ages came out much higher. And if you look at this peak, you see that it corresponds with Cornelia. You look at this peak, and it corresponds with Licinia. So if we find an asteroid, we can actually tell from which of the craters it comes on Vesta. Marcia is a much bigger crater, but it's too old in the sense that by now all the debris that was generated has been removed from the inner solar system. So we don't see that impact event. We see Licinia, we see Cornelia, we see Antonia. And there's also a smaller crater called Rubia sitting at that time, and that proved to be the source of this meteorite, asteroid 2818 LA. When the fireball came in, the meteor itself was very bright. It was, again, very well observed. This is a video from South Africa. But the asteroid was not very well observed. And so going in, I did not know where to look. I needed help from local gas stations, restaurants, establishments that had video security cameras that could tell me in what direction did this thing fragment at the end. And I teamed up with Oliver Moses at the University of Botswana in Mohun. We visited many establishments in Mohun and in Reekaps, and we were able to find some videos with shadows that allowed us to triangulate where to go, and where we had to go was the Central Kalahari Game Reserve. And this is one of my pictures. We scoured the area. The vegetation was significant, but there was a lot of sand, so it was quite easy to walk. A lot of poop, the sort that looks like meteorites, in this case from the Gemsbok. But the last day of our search, we were having breakfast in the morning, and we started searching. You can see on the right side there is our camp. And this picture was taken, I think, at the moment when Saricicek found its first meteorite. So he's standing there looking at it, I think, as the guy in the blue jacket in the middle of the picture. And sure enough, I had to poke it with a straw to make sure that it was indeed a meteorite and not Gemsbok poop. But this was a little piece of asteroid 2018 LA. And we had a lot more recoveries after that. After we came back in October, we knew a little bit better where to go. Fortunately, Mohutsebe Gabadiawa, who is leading our group, he was the one who found number 2, and then we very quickly found others, including the one I showed you on the video. And as you can see, all the meteorites look very different. They have light interiors, they have gray interiors, they have different colors and textures to their fusion crusts, but they all have this covering of glass. They all have this, what we call a fusion crust. And so that's really the thing you're looking for when you look for meteorites. And now we can even tell where it came from. So this asteroid Vesta, and this is the place, the Rubria crater. And we think this came from Rubria because it had very low solar wind ions, while the Saricicek one did. Antonia crater is on the slope in the Rio Silva Basin. So there's a lot of churning around, a lot of landslides. This crater is found on a tropical high. So I'm still very proud that I managed to not just get a paper published in Meteorics and Planetary Science, but actually have a lion on the front cover. I think this is the first time that has happened. And this was indeed one of my one of my other pictures taken during this trip. And you can see that the meteorite itself is just incredibly interestingly looking. So with that, I think I'll end my talk and open it for questions.
Let me see it. We have some questions here. Let me check. While we're waiting for there's one question here. I think this was answered already. A question from Dante De Jesus. Do asteroids have magnetism? Yeah.
Yes, they do, because collisions can create magnetic fields, and which is recorded in the in grains in the meteorite. It's very weak, so it is important to keep magnets away from meteorites if you really want to measure this. I must say it's not easy to do because there is a strong magnet in your cell phone. So if you come too close with a cell phone to a meteorite, then you're erasing that magnetic signature.
So I'm reminded of what you mentioned earlier, that we should not put a magnet on these meteorites.
Yes, thank you.
So to preserve the magnetism. And another question is here is Tony Dunn from San Francisco. I live in San Francisco and have about 100 deer nights a year. Would it be useful to you if I join the camera network? Yeah. From Mr.
Yes,
Tony Dunn
because
from San Francisco.
yes, you're local, so you can set up some cameras and immediately participate in the Camps California network here.
Yeah. Of course, I believe some of the Philippine attendees are also interested in joining.
Yes, you should. It's fun because you never know. You may be the lucky one catching something, and it's quite it's difficult, but it's very cool if you succeed.
Another question from Jerry. Jerry has been with us even before we started the webinar. Jerry Hilburn. His question is, how soon after a detection at Catalina Sky Survey does the ephemeris appear in the MPEC? And is there a special designation indicating a potential impact?
There is no special designation to indicate a potential impact. The information is usually spread via mailing lists and so on among observers who follow these things, because some of these cases all cases need follow-up, but these are, of course, of special interest to rapidly follow up on. So if you're doing asteroid observations and you're interested in tracking these asteroids and following up, getting astrometric precision and so on, then check the internet. There's ways to contribute to that.
Thank you. But a follow-up question here from Jerry again is there an alert system similar to the NOVA alerts that we can join to receive near-time reports and calls for observation? I do about 15 a week.
Yes. So both ESA and NASA have Meerkat and Scout. You can subscribe to. You can basically, you need to send an email. There are instructions how to become part of that, and then you will get the announcements. And I would say there is maybe one or a few per day, So it's not, you get a lot of false alarms, a lot of things that turn out to be nothing or turn out to be satellites and whatnot. But you have to, accept. If you accept that, then occasionally you'll see something that you think, "Well, oh, that looks good, that looks promising." And then when somebody is alerted, and like in this case, the observers themselves thought that this was an interesting looking object, then you'll see more emails and more certainty.
So sorry, but there's a question again from Jared. Send where? Where do we send this?
If you Google, for example, ESA Meerkat asteroid guard, it will take you there.
Okay. Thank you. And then a question from Laura May Abram. Hi, is there any way to plot the entry angle and other orbital elements of past events? For example, something like the event that created Barringer meteor crater in Arizona, perhaps through crater shape?
So with impact craters, it's a little bit difficult because the moment a rock hits the ground, all that energy is released, and that then while the rock punctures into the ground and is stopped, that's basically where you release all the energy. So it's more like a sort of a point explosion. You can't see the direction that clearly unless it's really shallow, in which case you can. But then, of course, with Barringer crater such a long time ago that we don't know the entry speed that well. For other objects, these games have been played. So, for example, Tunguska in 1908 has a lot of visual accounts, which are in Russian, but with Google Translate, you can read those Russian accounts and you can get your own opinion from all the different descriptions that were made of the meteor. And I think that for me was very illuminating because it, in my mind, showed that this object was going very fast. Unlike Chelyabinsk, 19 kilometers per second, this thing was faster. I think it was around 27 kilometers per second. The reason I think that is because that would be sort of the speed corresponding to something coming from the asteroid belt, from the direction this thing was traveling. And if you read the stories from Tunguska, they don't describe this really thick billowing cloud that Chelyabinsk left behind. They more describe an asteroid moving fast in the sky and leaving a thin trail behind. And so that also indicates that this thing was moving a lot faster than Chelyabinsk. And so it's better if you set up a camera and we get this trajectory recorded, then we can really calculate the numbers.
Thank you. And I guess it also helps that a lot of people now have cell phones with them, and
Yes,
they can do video recordings of this when they see it.
Yeah. Yes, exactly. For this case, for example, the video recorders are really nice because we already know the trajectory. We've seen the asteroid come in. We know how it was traveling through the Earth's atmosphere. So the video records show us the energy, the position profile, so how the thing brightened and so on. If you have a fireball that people catch on their dash cams on their cell phones, like we did with Chelyabinsk, then you have to make an effort because you have to then figure out the directions in the phone and do that right. And in that case, it usually helps if the camera is fixed. So doorbell cameras are better than dash cameras from a driving car, that sort of thing. But we try to do that. And so far, about 18 meteorite falls have been recorded that way.
Thank you. Regarding related to that, I think is has any work been done? This is from our panelist, Mr. Jun Lau. Question is, has any work been done to see if the atmosphere has any changes in chemical composition, even if it's light, during meteor showers?
Yes.
Yeah.
we try to do this during the Leonid. So there is actually a deposition of meteoric metals happening all the time. A lot of it comes in from mostly sporadic meteors, and that are really small, too small to give us visible meteors. Most of the mass influx is at those 100 micron or so sizes, and they create what we call the sodium layer that gives sort of this orangey glow high up in the atmosphere that you can see in space images as a glow surrounding the Earth limb. But it's difficult to see the effect of showers because it usually doesn't match up, doesn't stack up well against all this other stuff coming in. But with the Leonids, we tried to do that, and there were some hints that maybe we saw something, but yeah, that's not so clear. By the way, on the previous question with the video security cameras, the thing to remember is that many video systems don't keep their video very long. So if you have some of the older systems, you need to make sure that you find the fireball and that you then save that data. And for that, you need to know exact time when this happened. So when people report a fireball, do check your watch, do check your phone, report the time that you know when the event was, because that can help other people find records of it as well.
Thank you. And this another video question from camera system question from Tony Dunn. Does the data from the camera system help you discover new streams?
Yes, and that's currently my interest with the cam system. We are monitoring the sky constantly. It's really a video surveillance day, night after night, in the hope of finding unusual showers. And when that happens, it adds to our understanding of the inner solar system. And we do this a few times a year that something unusual pops up.
Question from Jerry Hilburn. Concerning observations, is there a filter recommended for telescope observations, such as Sloan R or G, or the JCB or B, or is the only interest in astrometric measurement?
No, most observers are focusing on astrometry because it's easy to do. But we tend to get enough observations of asteroid astrometry to get a really good fix on where the trajectory is. This case, for example, had 9 hours of warning, so there was for 9 hours people could track this thing and follow it. The problem is that that other types of observations there is actually little time for. So if you have a telescope that can do spectroscopy, for example, that is really needed. We need to characterize this asteroid while it's still in space. Radar, all sorts of infrared, all sorts of ways to characterize this asteroid while it's on its way in. That would be really helpful, because then we can make these most direct connections between the asteroid in space, like most asteroids we're looking at, and the fireball and the meteorite that we find in the ground.
Well, Jerry said he has a WAP shell spectrometer.
Cool. Yeah.
Good.
So the nice thing about these little asteroids is that they can get pretty bright when they are really close. So just before going into the Earth's shadow, I think TC3 was like 13 magnitude or something. So if your scope can handle that, then take spectra of this thing.
Thank you. There's another question here. I think it's more for layman. A practical question is, how can you tell a true meteorite from an ordinary terrestrial rock, or if I may also add, from a poop?
Yes. So poop is one of the 5 meteor wongs. Basalt, asphalt. Asphalt is a very nasty one. What is it? Charcoal, poop, and I think there was one other one. So there's five things that people typically confuse with the meteorite when they're sort of wandering around. But the one thing that a meteorite has, and almost nothing on the Earth has, is a fusion crust. It's really this layer of glass that surrounds the rock. it's very different from desert varnish. So if from weathering the rock on the outside, that looks quite different. A fusion crust is really a thin layer of glass, and you can look at pictures on the internet to see how fusion crusts look like, and that's the thing to look for. So not how it looks inside, but whether there is this fusion crust. And usually what you do if you look for meteorites is you look for things that are out of place. So a rock that really stands out, that is unusual, that there are no other examples of in the environment, that's an interesting rock to consider. I have had experiences with meteorites that did not have fusion crusts, because that particular meteorite was so shocked that it had basically been turned into glass, so it didn't hold on to its glass. You find weird cases, but typically the best thing to go for is looking for this fusion crust.
Thank you. Here in the Philippines, we a lot of. Are you familiar with tektites? People
Yes.
collect tektites.
Oh,
yeah. So
Yeah.
how is it different from a meteorite?
So
Yeah.
a tektite is terrestrial soil that was melted by an impact or by an airburst. And we think the impact area now has been identified as an area in southern Laos, below the Bolaven lava field. There is basically a big lava field that covers the whole impact area. But in that whole area, you can find chunks of glass from this event, and that material that happened about 790,000 years ago, that was scattered all over the southern hemisphere, Australia, even into Antarctica. There's a lot of really nice pieces found in the Philippines. We have a tektite field in the US as well. You can find pieces of it in southern Georgia and in Texas and Louisiana, and those are called badiosites, and that was from an impact that happened in Chesapeake Bay, which is it's now deeply buried. It's a very old crater, about 35.5 million years old. But there was a big impact at that time, and the way you find these tektites is just go to where riverbeds from that era were exposed, where the soil from that time is exposed, and then look for little dark rocks that are translucent. If you hold it against the light, you should basically see that it's glass.
Mm-hmm. So physically, how is it different from a real meteorite?
It doesn't have a fusion crust.
Oh, yeah. Okay.
Doesn't have a fusion crust. I can. Just 1 second. Let me show you.
Oh, you have a box of meteorites
I have
there.
my show and tell box. So this. Oh, let's see if it's maybe you can put me on the big screen.
Yeah. How do you wait?
Yeah, just unshare the.
Unshare. Stop share. There.
Yeah. So this is a meteorite, and you see that you see how the rock is covered in the glass, and there are little chunks broken off in this case.
Oh, nice.
So you can look in the inside. Yeah,
so that you can see a sheen or like that, like looking at a glass cover. I mean.
Yeah, it's a little bit shiny. It's not really. The color can be very black. It can be brownish or gray. But the thing to look at to notice is that it's really it really covers the stone. It's not a varnish. It's not an etching a seeping into the rock. It's really a layer that got really hot and was immediately blown away by the air. And the inside of the rock doesn't get very warm. So when these rocks fall on the ground, you can also hand warm. So if you have a tektite, see if I can. I don't know if this one, I can hold this with my hand because it's not a meteorite. So here, this is a glass.
Yeah.
And it has this weird pattern on it that you see comes from basically weathering, so when it's in the soil. But in this case, it was a meteorite that was very quickly spinning, and so there were two pieces that one piece broke off. So that's why it has this droplet shape. These are called these are all from the sort of meteorite, some sort of tektite that you find in the Philippines.
Thank you.
And this one here is what you find in Texas. This one I found myself. Yeah, you can see a little bit that it's translucent. That's really a glass. It has the color of beer glass. If you have if you're in the Sahara Desert, it looks like this. It's Libyan desert glass. And the big impact in Germany, called the Ries crater, created these moldavites. And so this glass is more greenish in color. It depends on how much iron there is in your rock. So, but that's yeah, that's what a tektite is.
Are you familiar with any meteorite discoveries in the Philippines?
I'm not. I will be, hopefully, after this talk.
Thank you. Another question here thank you for that, for educating us about the difference between,
another hour
because
show.
what I have a lot of tektites and a few meteorites.
Okay.
So from Andrew, our panelist, his question here: as more of these asteroids are getting discovered prior to their entry into the Earth's atmosphere, do you think that it is necessary to communicate these incoming asteroids on the NOTAMs of flying aircraft so pilots wouldn't be surprised and be fearful if ever they would encounter a big fireball in mid-flight? So
So in a way, we've done that with TC3, because asteroid TC3 was discovered 21 hours before it impacted, so it's a lot of time. And at the time, there was a meteorologist, Jacob Kuiper, in the Netherlands, who worked for the Royal Dutch Meteorological Institute, and he was supposed to brief his pilots on weather conditions during that time, and he included information on this fireball that was supposed to come. And so there was an airplane that flew from Southern Africa, I believe, over Chad at the time of the TC3 impact that saw the fireball in the distance. It was like lightning. They saw like 3 flashes of light. So if the meteorites fall down, it takes a few minutes to fall down, but there are pieces coming down. And so if that information can be shared effectively in time, then that's probably a useful thing to do.
do we have any other questions from our panelists? Edwin?
Yeah, actually I do. But first of all, I'd like to thank Peter for sharing his expertise on meteor showers with us. And it was a really fascinating talk, especially sharing your adventures in searching for these meteorites. So if I understand correctly, you also found some meteorites in Antarctica. Did
Nope.
you?
No,
No?
I've never been searching for meteorites in Antarctica.
Ah,
But for me, it's not about the meteorite per se. It's about the connection with the meteor and the fireball. That's for me the interesting part. That's where you make this into astronomy. And so for all the meteorites found in Antarctica, we do not have orbits. We do not have approach orbits. So what we can do with our cameras is something unique, something really where we can add data on trying to figure out where the meteorites are coming from, which asteroid debris field corresponds to what meteorite type. That's something that comes from our cameras. It doesn't come from the it's missing when you go to these Antarctica or to desert areas and so on, where a lot of meteorites are being found.
now, regarding questions, I do have a couple. The first one is you mentioned during your talk that you don't recommend putting a hand magnet close to a meteorite specimen because it can erase the magnetic record of the meteorite. What about if you use a metal detector? Would that also erase the magnetic record?
I don't know. But I do know that metal detectors normally is not a useful tool for looking for meteorites, because a metal detector you have to hold in your hand and you can cover basically only a small surface area.
Hmm.
While if you walk and you just look around, you're covering a much bigger area with your eyes. And if your eyes doesn't notice the thing from standing out from other rocks, then the metal detector wouldn't work either. There's only one case that I know of, that was the bolide, the Benesov bolide in the Czech Republic, where they had a massive bolide. They calculated where it should have fallen. The problem is always to get a good grasp on the winds, because the winds blow the rocks off course, and so you have to calculate exactly how much they did. And initially that wasn't done right, and so when years later it was recalculated, they found that a meteorite should have fallen in an agricultural field. By that time, farmers had gone in and had plowed under the meteorites. And so there you go with a metal detector, and now you go and look and they found some meteorites. They found also different types of meteorites. So some were LL, some were H. And that's very exciting, because that was sort of the second case where there was a mixed bag of meteorites coming from, one fall. And so, and that's another interest I have, is that most meteorite falls, people find, one piece, but what you really need to do then is to try and find more pieces to really get a complete picture of what was in this meteorite, in this rock that came in.
Thank you. My other question is, I've read that the NASA's DART mission, the asteroid impact mission, has the potential for producing a new meteor shower.
Yes.
What can you say about that?
So yes, you see all this debris that goes flying, and so that means that now you have created a meteorite stream. In this case, we know where it is, but in most cases, you want to avoid doing that, because if you create a meteorite stream, as I said, even if that little rock just sits there and the Earth runs into it, then that's 30 kilometers per second. So if you can avoid throwing around debris while you are in space, then you're keeping your satellites as safe as you can. There's of course natural debris, but in this case, the total amount of material isn't that big, and so on. The main concern is when people are talking about asteroid mining, because if you go to asteroid mining and you're not keeping yourself absolutely clean, as in put a big bubble around your asteroid and keep all this stuff with the asteroid, then you're going to create meteorite streams, and that's potentially an impact danger for other satellites.
Great. Thank you so much.
There is a comment here regarding magnetism. There is by Laura May Abram. There is a device invented by Cerejes called the MET or meteorite meter to not damage the magnetic information.
It does not. No, that's a device that measures the magnetic susceptibility, and it doesn't change the magnetism of the rock. What it basically measures is how susceptible that your rock is to a magnetic field. And in it is very useful, because it can tell you in the field what type of meteorite you're dealing with, to first order. And so it is a useful device to have.
Thank you. Peter, do you have any comments or questions? Peter is our local meteorite enthusiast.
Yeah, first of all, congratulations, Peter, for that wonderful talk. I learned a lot from you. and I have like been much more interested doing meteorite studies and meteor showers as well. Now, for the record, for the benefit of everyone also who are listening out there, um, are meteors produced by friction or pressure from the Earth's atmosphere? Because there are a lot of feedbacks coming from schools and other people, and they tend to know what really causes meteors, if
Yes.
it's friction or versus pressure.
Friction is basically what creates the meteor, because friction is basically transfer of heat by collisions. The pressure is what breaks the meteoroid. So they both play a role. Yeah, there's no such thing as burning. People, it looks like burning, but it's really more. You create a gas and plasma, and more like a sodium lamp than a incandescent lamp.
And my second question would be like, when observing meteor showers, when a particular meteor passes by, how do you um, uh, refer it as part of a meteor shower in terms of distance from the radiant?
Yeah.
Yeah.
So a meteor shower is caused by a meteoroid stream, and that basically means the particles move in parallel orbits.
Right.
So they're going in the same direction. So you're standing in the middle of it, and you're seeing this stuff come from a certain direction. That means that you see stuff above you, sideways, a few other ways, and so on. It all comes, if you go backward, it comes from this one direction called the radiant.
The radiant.
And the position of that direction, the apparent radiant, that's what we name meteor showers after. So the Perseids would be meteors coming from Perseus, Geminids come from Gemini, and so on.
Yeah.
And so if you see the maps that I'm putting out from all the triangulations we're doing, you see points on a celestial sphere, which are those directions of the radiant. So you see these blobs where you have a lot of meteors coming from that same direction with the same speed, and that's a meteor shower. To use that for your observation, so if you can look at it on your phone. So if you're out in one night and you see a meteor, then you can basically track the path back along the sky and see what constellations it passes through. And then you can look on your phone and you can check out if there is any meteor shower that is along that path. And it also tells you if the meteors are fast or they're slow. And so you can use that to identify the meteors you're looking at. And that's a very cool thing to do, because meteor showers do look different for various reasons. So it's an interesting that you can actually identify what the source is, what the parent body is, and whatnot.
Yeah. Does the particular meteor need to be how far from the radiant to consider it as part of the shower? For
No,
example, so
it
it's
could be on the
regardless.
other side of the. It could be on the other side of the sky, and it could still come from that shower. So as long as the direction is the same as the other meteors are.
Thank you. Thank you.
Yeah.
Thank you, Peter. Okay. So thank you so much again, Peter. If there are no more questions, thank you for your patience and for your beautiful talk, wonderful talk. We all learned a lot. And we are looking forward, or hope you can visit us here in the Philippines in the near future.
Yes. So next time when a small asteroid lands over land, then hopefully I can be of some help as a guide to help you find pieces of it.
So
Peter, you'll have a lot of volunteers.
Excellent.
Well, last matter, how do we acquire actually, or how can our institutions acquire the camera for monitoring or apply to be in the camera network? Is there
Yeah, there are a couple of camera networks that you can use. You can participate in CAMs, or you can participate in the global meteor networks, and a new network that is really expanding greatly at the moment. If you go to the CAMS website, as cams.seti.org, then you will find information where to get to this different camera networks. You can also Google CAMS SETI, for example, or Global Meteor Network, and get information on those.
And before we let you, because it was mentioned, SETI was mentioned. So what exactly does, what's your involvement with SETI?
So I'm employed with the SETI Institute. I do projects for NASA, and that's how SETI has operated for many years. So we are basically supporting NASA in its missions. And my emphasis has always been on the real extraterrestrial visitors we are getting, and that is the little bits of rock that are coming in the Earth's atmosphere, and that tell us so much about space.
Thank you. We would not like to let you go, Peter, but of course, we do have to eventually let you go in this presentation and this talk. But before we let you go, and thank you again so much, we can never thank you enough. Kindly allow us to present our ALP Certificate of Appreciation. And as you can see, it reads, this certificate is presented to Dr. Peter Jenniskens, PhD, for the webinar entitled 2024 RW1 and the Importance of Small Asteroid Impacts, held as part of the ALP Astronomy Expert Speaker Series of 2024, given this 29th day of September. Signed by our president, Mr. James Kevin T., and yours truly, Dr. Jose Francisco Aguilar. Thank you again. Happy meteorite hunting in the future.
Thank you, Peter. We appreciate.
Thank you, Peter, for the good webinar.
Pleasure.
Yeah, appreciate it.
Thank you.
Thank you.
Thank you very much, and have a great evening.